Welcome back, class. So today we are going to start into chapter 4. And in this chapter, we're going to be looking at chemical reactions. So initially, we're going to look at how to balance chemical reactions. And then as we move through the chapter, we're going to look at how to quantitatively determine how much of the different materials in a reaction that we either can make if we talk about a product or that we need if we're talking about a reactant. And to this, we're going to utilize some of the concepts that we learned in the last couple of chapters, working with moles and molar mass. So we're going to apply some of those things to quantify what we see in a chemical reaction. So without sort of further intro, let's jump right into looking at balancing chemical equations. So, first of all, what is a chemical reaction? Well, a chemical reaction simply describes chemical change. Using a type of shorthand. Now, we're going to talk about some of the ideas that we use to convey this shorthand and some of the information that we need to understand to do that. So, to write it out, we always write it in the form of the types of matter that we begin with. So we call this the reactants. And we use an arrow to show the movement or the change. So the reactants will react to change into what we will call the products. And so as we read from left to right, we have our reactants, whatever form of matter that takes on, reacting to change into, again, new type of matter, right? That's the essence of a chemical change, and what we call the products. Now, as we write this out, we're going to use certain types of conditions or standards that we're going to always write it this way. So the first thing is we're always going to use chemical formulas. We don't use names. When we write these out, we always use the formulas. Next, we should always put the state of matter. So if we look up at this table here, we see there's 4 options for our state of matter. We can have a gas, a liquid, or a solid, abbreviated by their letter, or the 4th one, which we will use quite often, is an AQ, which stands for an aqueous solution, right? So, which we'll get much more into talking about next chapter, but this is a water-based solution, so our material has been dissolved into water. So we're going to list the states of matter, and the reaction will also show the relative number of product and reactant that we have. So it's going to show us the relative numbers of the product and reactants, whether they be, elements or compounds, right? It's going to show us the relative number in terms of the relative amount. And we're going to do this by using something called coefficients. And these coefficients will appear in front of each reactant or product to specify the relative amounts. Okay, so with that sort of basic idea, we're going to start looking a little bit more into these chemical reactions. Now, maybe a first thing we want to look at is how do we know if a chemical reaction is taking place? Well, there are certain signs that we can visually observe or we could read in a description that might indicate a chemical reaction. Now, I will say some reactions will have more than one of these, some will have none of these, and so there is no one way you can tell, but sometimes they're hints. So, there's some physical things that we can look at. So we can look at, do we see a solid forming? Or do we see a gas being produced? Or maybe there's some energy ideas. Maybe we see light being given off. Or maybe we feel heat being given off, like we did when we burn something, for example. Maybe we see a color change. So these are things that can tell us that we may have a chemical change or a chemical reaction occurring. Okay, so now let's look at a potential chemical reaction. So it asks me to write the correct equation for the reaction between methane and oxygen gas to produce carbon dioxide gas and water vapor. So methane, right, and this probably should tell us it's methane gas at this point. But methane, remember, is one of those simple organic hydrocarbons that we talked about at the end of the last chapter. It's the main component of natural gas that we use for heating. It has the formula CH4, right? So we have methane gas plus oxygen gas. And so notice, right, we have to remember that oxygen is diatomic, and we've noted that both of these are gases, right? So right after them. So we note the states of matter there. We have our arrow, and our products here are going to be carbon dioxide, right? So we need to be able to write the formula of carbon dioxide gas plus water vapor. Now, of course, we need to be able to write the formula of water, and of course, vapor is just another way to tell us that it's a gas. So now we've successfully written our chemical reaction. Now, the one sort of last and maybe the most important or second most important, right? We have to be able to predict or write out the reactants in the products, right? But the second thing is to see, is it balanced? And what do we mean by this? Well, remember, all of these reactions are going to follow conservation of matter, right? So way back even with John Dalton, right, we talked about in a chemical reaction, matter is conserved, right? That we don't change, we don't lose mass, we don't create mass. And to go along with that, right, we also saw that elements don't change in a chemical reaction. So, if we have a carbon atom, right, it's going to stay a carbon atom. And the way that we ensure that conservation of matter is conserved is that the reaction must have what we call atom balance, which simply means we have to have the same number of atoms of each element on the reactant side as we do on the product side. So we have to, if we start with 2 carbon, we have to end up with 2 carbons on the product side, etc. And this is where these coefficients come into play, right? So we are going to use the coefficients to balance this out. Now, one thing I will note here, and I will put a little asterisk down here, never change the subscripts. So in other words, when we've written this out and we have, say, CO2 or CH4, we never change the formula, right, as in an effort to balance, right? So we never change this to CH5 to make it work, or CH3, right? The only thing we ever change are the coefficients. And these are, again, numbers that we put. We're going to put them in front of the reactants and products to show, again, the relative number of reactants and products that we have. So let's go ahead and try to balance this equation. So I'm going to rewrite it here. So we have CH4 gas plus O2 gas. Give me CO2 gas plus water gas. Now, as we go about balancing them, there's a couple of tricks we can use. There isn't a perfect system because everybody sort of approaches it a little bit differently. We think about these things just a little differently from each other. But some hints that will kind of get you on the right track is always balance first atoms that appear in just one place on the reactant and the product. So for example, carbon appears here in the methane and here in the carbon dioxide. And leave elements that appear in more than two places till the end. So like oxygen appears here in O2, but it appears both in carbon dioxide and water. So it appears in 3 locations. Now, this is just going to save us some time at the end and maybe reduce the number of times that we have to backtrack and change. But otherwise, we're just going to approach this in a sort of systematic way. We're going to do some other examples after this that we can and I'll give you some more hints along the way. But let's just check these. So if I first start with carbon, let's say, I have 1 carbon on the reactant side and 1 carbon on the product side. So it's balanced. It's all good. So let's do hydrogen next. So I have 4 hydrogens here, right? But I only have 2 hydrogens over here. So how can I possibly get the same number? Well, if I have 2 hydrogens in each water molecule, if I were to put a coefficient of 2 here and say I have 2 waters, well then I have 2 times 2, or a total of 4 hydrogens in these 2 waters. So now I have 4 hydrogens here, 4 hydrogens here. So now the carbon's balanced, the hydrogen's balanced. Well, let's go back and look at the oxygen. So if we look at the reactant side, we have 2 oxygens from O2. On the product side, we have to add these together, right? We have 2 from our 1 CO2, and we have 2, 1 from each of our 2 waters. So we've got a total of 2, 4. So we have 4 oxygens over here and 2 over here. Well, if I have 4 and I have 2, one simple way that I can balance that is simply to put a 2 here, and then I have 2 times 2, or 4 oxygens over here, and 2 and 2, 4 oxygens over here. Now, like I said, different people will approach these differently. Some people will write it out like this. Some people, and they show this a little bit in the book, you can write it out underneath it as you do it, or as your final check, just to sort of tally and actually write it out. And so, again, there is no perfect process. It's going to be a little different for each person, but the key is we get to the correct balanced equation. Now, let's look at these coefficients, and what do they mean? Well, they tell us, again, the relative number of reactants and products. Now, let me note that if there is no coefficient, or if the coefficient is 1, we don't show it, right? So we don't write 1 here, right? If it's no coefficient, we just assume it's 1. So these coefficients, the 1, the 2, the 1, the 2. They give us two pieces of information, or they can be sort of interpreted in two ways. Right? They can tell us the number of atoms or molecules, depending on if we're working with an element or a compound, of each material. So this tells me that one molecule of methane reacts with 2 molecules of O2 to give me 1 molecule of CO2 and 2 molecules of water. And it gives me those ratios, right? It says for every 1 methane, I can make 1 carbon dioxide, or I can make 2 waters. Right? Now, more importantly for us, going forward in this chapter, is that it will tell me the relative number of moles of each material. And so, since we typically will deal with large quantities and we quantify using the concept of moles, these these coefficients give me the ratio of moles, right? They say that 1 mole of methane, well, it needs to react with 2 moles of oxygen to give me 1 mole of carbon dioxide and 2 moles of water. Okay, so now we hopefully have the basics of balancing equations. Let's do a couple practice. So let's look at our first one. Solid potassium chlorate yields solid potassium chloride and oxygen gas. Now, in different problems, you'll be presented with this information in various ways. Sometimes they'll give you a description, like a paragraph, like maybe we saw in our first example. Sometimes they'll give you something like what I have here. Sometimes they'll give you the formulas, right? So we need to be prepared to do this in whatever way necessary. So, solid potassium chlorate. So first of all, we have to know, what is potassium chlorate, right? Well, if we think about it as, we know it's an ionic compound, right? Because it has a metal in it. We hopefully recognize chlorate as one of our polyatomic ions. So if we think about potassium in an ionic compound is K plus 1, right? It has a charge of plus 1. The chlorate polyatomic ion is ClO3 with a minus 1 charge. So to write this compound, right, we have to balance our charges, so 1 and 1. So it's going to be KClO3, and we were told that it's a solid. So solid potassium chlorate. And that reacts to form again solid potassium chloride. So again, an ionic compound, the metal and the non-metal. So we got K plus. The chloride is the iron of chlorine, right? And we know that is always a minus 1 ion. So again, to balance the compound, 1 and 1. So we got KCl solid. And then plus, what I'm told is oxygen gas, remembering oxygen is diatomic, and we have the gas. Okay, so now we've written out the basic equation here, but what about balancing it? Well, let's just start. So we'll start with potassium. We have 1 here, 1 here, all good. We'll go to chlorine. We got chlorine, 1 here, 1 here, all good. We got oxygen, we got 3, and we got 2. Uh-oh. This could be a little tricky, right? Because, in the last example, we had 2 and 4, right? So we could just simply put a 2 and double it. Well, there's no way that I can put a number in front of O2 to make it match 3, because 1 is even, 1 is odd. So the trick here is we're going to look for the lowest common, you want to call it factor or that both will go into. So if I think of 3 and 2, the lowest common factor that both can go into is 6, right? So in this case, that's 6. So in order to get 6 of these, 6 oxygens over here, I need to put a 2. To get 6 oxygens over here, I need to put a 3. So now we can see I have 2 times 3 are 6 oxygens, 3 times 2, 6 oxygens here. Now, since I changed this, that also affected my potassium and my chlorine. So now I have 2 potassiums. So I got potassium here, so I'm going to put a 2 here. Gives me 2 potassiums. I also have 2 chlorines. Well, the 2 also changes the chlorine. So I go back and check it. I have, on each side, I have 2 potassiums. I have 2 chlorines. And I have 6 oxygens on each side. So all balanced. Let's do the next one. So then I'm just going to use my description to write out what I know. So I got iron. Let's use a different color here. I have iron, metal, right? So that tells me it's a solid, plus aqueous copper 2 sulfate, right? So we should identify this as an ionic compound again, made up of copper 2 plus, right? That's what the copper 2 tells me. Sulfate, again, a polyatomic ion. So we're going to, if we remember that sulfate is SO4 2 minus. So if to form the compound here, we have plus 2, positive 2, so we're going to have 1 of each. So this is going to be copper SO4. AQ is for aqueous. So it's aqueous copper 2 sulfate. Now on this side, we're going to have aqueous iron 3 sulfate. So iron 3, right, is iron 3 plus. Sulfate again, SO4 2 minus. So how do I write out this formula? Well, I have 3 and 2. I can cross over here. And so my Fe subscript becomes a 2. My sulfate subscript becomes a 3. And so remember, when we're writing with multiple polyatomic ions, we use parentheses to show that we have 3 of this SO4 group. And again, it's aqueous plus copper metal. Okay, so now we have our basic equation. So now we just need to balance it. So again, I start with the iron. I got 1 iron here. We got 2 iron here. So I'm going to have to put a 2 here to balance my iron. Well, let's try the copper now. I got 1 copper here, 1 copper here. All good. Now, a little trick. Since we have a polyatomic ion, that polyatomic ion hasn't changed, right? It's a sulfate. So if the polyatomic ion is the same on both sides, so up here, right, in that first reaction, the chlorate changed, right? It broke down. So we couldn't do this. But here, the sulfate is still sulfate. So we can balance it as a group. So remember, we can balance polyatomic ions as a group if they stay together. So let's look at that. So we have 1 sulfate over here, and we have 3 sulfates over here. So if I put a 3 here, that will give me 3 sulfates on both sides. Now, of course, that also changed the copper. So now I have 3 copper. So I go back to here. I have 3 copper. So if I double check, on both sides of the equation, I have 2 Fe's. I have 3 Cu's. And I have 3 sulfates, SO4s. So all nice and balanced. Okay, well, hopefully this has given you some good practice on balancing equations. Again, like a lot of things that we're doing really early on here, like naming and so forth, practice, practice, practice. The more equations you balance, the easier this will be.